everybody. This is Eric Andelin, Senior Workflow Advisor with SimActive, and you're joining me for my interview. Does better positioning really improve mapping accuracy? And with me today, I have Mohammed Mostafa, Lead Technology Authority for Mobile Mapping at Trimble Applanix. Mohammed, please say hi to everybody and give them a little bit of information about yourself and your company.
Thanks, Eric, for the invitation. It's a pleasure to join you here today. Hello, everyone. My name is Mohamed. I'm with Trimble Applanix, as Eric described, lead technical authority in mobile mapping. And mobile mapping includes airborne, crewed or uncrewed, land and indoor applications. My background is sensor fusion in the form of integrating multi-sensor systems on the software and workflow front. I went to school in engineering, surveying back in Alexandria, Egypt, and I graduated 1991 with a bachelor's degree. Then I moved up to Calgary, Canada, where I did my master's and PhD in 1994 and 1999. And once I graduated my PhD, I joined Trimble Applanix, where I started to learn from everybody I worked with to actually develop the right technology in the form of the right product. So this is where I come from, my background, and I'm looking forward to this conversation here today.
Very good. Interesting note that you had worked on that Katrina, or the system for that Katrina imagery, because I remember when they captured that so many years ago, and one of the things that they did was they released it to the public to do, whatever type of testing or whatever type of processing they wanted to do with it. And I was impressed at, even then, it was like, whoa, these photos are coming in the right place, which was not something you would normally expect at that time. So that was really interesting. While we're at it, let's go over the topics we're going to cover, and they are choosing the right positioning systems, understanding their integration with sensors, importing positional data into Correlator 3D, and then quantifying achievable accuracies. Let's start off by talking about choosing the right positioning systems. What are all the components of a positioning system? What makes one different than the other?
That's an excellent question, Eric. A positioning system could simply start with a GNSS or the American GPS and the additional systems, including the Russian GLONASS, the European Galileo, and then the Japanese, Chinese, and Indian systems that ends up now adding up. The total number of satellites available today are over 130 satellites operating on 11 different frequencies, which is an abundant type of information for any positioning system. So the challenges today are actually to leverage all of these streams of satellite positioning data into one position, basically, of an aircraft or a drone or a mobile mapping vehicle on the ground. Now, in addition to that, there are other positioning technologies that could definitely add to the mix, including inertial technology, which measure the rotation of an aircraft or the orientation of any moving vehicle in 3D space. And that orientation becomes a necessity in some applications, such as radars and LiDAR, or an advantage to some other applications like cameras. So, for example, for a camera, you don't need to know the orientation of the camera up in the air 100% of the time, unless your application necessitates to have that information. For example, if you're doing corridor mapping and you're flying very narrow corridors, like covering a highway or a freeway for tens of miles at a time, so you end up flying one or two flight lines. That is not going to work well in the area triangulation world. So AT is not going to help when you're flying one line or two lines. But if you have inertial system on board, included in your positioning system, it will do a fantastic job. And you're going to end up actually delivering in a DG or even in an integrated sensor orientation environment, or even an area triangulation environment, but there is measurements from the inertial sensor, then the one strip or two strips of imagery will actually work in area triangulation very well. So that's another thing. Like we looked now at using lidars. The lidar systems will come with the inertial GNSS system integrated into it. It actually comes in the box or in the system. If you have a multi-head camera system, they come with the inertial GNSS built into it as well. And then if you are building your own payload on board a drone or an aircraft with a single camera, you have the option of having GNSS or GNSS inertial integrated system. And as we mentioned, if you are tackling corridor, if you are doing challenging applications where you want to fly free like a bird and do rapid response like NOAA and many other organizations in the United States, they prefer to fly free of the necessary geometry that area triangulation is comfortable with, such as blocks of images in the form of rectangles or boxes of in a square size, where the geometry is good enough for area triangulation to do its magic. But if you're doing some other applications that you cannot actually do a box of images in the form of a rectangle or square, such as forestry, mining, and so on and so forth, construction, surveys, then you need to launch the inertial GNSS systems to help you accomplish that. Now, when inertial GNSS kicks in a system, they enable you to do more than the standard simple area mapping process. And in the meantime, they add a little bit of more data that kind of makes you free of the dependence on the ground. So you kind of get all of the control that you have on the ground, you put it up in the air because you invested in having your control up on board the aircraft or the crewed or uncrewed. It doesn't matter. It's the same thing. So when you invested in that initial capital where you have inertial GNSS on board your vehicle, either crewed or uncrewed, you freed yourself from having any dependence on the ground anymore. So it's practically as if you're doing satellite remote sensing and capturing imagery from satellites. So now, with that said, the science and art of geodesy kind of kicks in now in the conversation, because geodesy is the way we ended up kind of enabling the entire planet to be possible to be mapped on a piece of paper back in the day, hundreds of years ago. So when we did the mapping, we ended up doing the mapping on paper, not really on digital as we have recently done. So producing maps on paper of a curved Earth had to, people had to be innovative to map that curved planet on a piece of paper, which is a plane, and that is the science and art part of the geodesy called map projections. And map projections does a great job, but it adds distortions. Nothing comes for free. Those distortions actually necessitate that when you are producing maps and you have all of the sensors up in the air, you don't have any access to ground control. It gives you an amazing alternative to using ground control by using your airborne sensors. Then when geodesy gets in the way to produce things properly, to fit the map on the right spot on the ground, you could use one control point to remove the influence of all of these distortions from map projection, and we call that datum shift. So the recipe is, if you're using LiDAR or radar, it comes with the necessary inertial GNSS. If you are using cameras, if you have multi-head cameras, it makes more sense to have inertial GNSS. And all of the systems around the globe, the professional grade manned aviation systems from Vixel and Phase 1 and Hexagon, they come with their inertial GNSS baked into it. So the system is complete with the inertial GNSS component. And if you are dealing now with one single camera or a new payload that you're designing for a drone that includes a camera or more, a lidar or so, or both, like a camera and a lidar system, you already have your GNSS inertial system
Bring
and a
on.
lidar. If you're doing one single camera, that's the last piece to address. It depends on the application then. So if you have one camera you're developing as a payload on board the drone, add a chip of inertial GNSS, it will have that influence of freeing you from being dependent on the ground at all times. Whether or not to use area triangulation, if you're doing area corridor mapping and have inertial data, which gives you the roll angle, that roll angle actually, when you're flying a single line, is an issue with area triangulation. But if you capture that in the form of data you acquire by your inertial system, the area triangulation would be way more comfortable to produce very, very productive and accurate mapping products.
Yeah, it's I look at it this way. You could use a small format camera like a Sony or something like that, off-shelf camera, that's fine. But when you spend, 100,000 or more or $1 million on a camera, the inertial measurement system, the IMU, the positioning, all of that, that's nothing. You've already made the investment, so um, use it to the maximum extent possible and carry that equipment with you. And like you said, with LiDAR, you have to have it. There is no LiDAR without an IMU. Um, so that's certainly a thing. And part of that is because of collection rate. And you could tell me a little bit about this. How many times are you capturing that position? And then we also talk about LiDAR, how many times it's spinning, collecting points. It's something you have to have.
Absolutely. Like, for example, when you're acquiring data, you're acquiring multiple streams of data. So GNSS provides uh, two important streams of data. The first one is timing, because GNSS or GPS in particular was the very first global timing system. All of the timing systems around the world have been like satisfying, but they were local. The first one that is global is actually GPS, and the accuracy of GPS timing is really, really high. It's beyond a microsecond, so it's actually closer to a picosecond today. Timing means that you can synchronize multiple sensor data coming from LiDAR or cameras or any other sensors, or a group of sensors on board your mapping vehicle. And that's what takes place in the mobile mapping systems. They have like multiple lasers and 6, 7 cameras and some other aiding sensors for localization and so on. And all of those are synchronized in time using GPS signals. Now, the second feature that GPS adds, or the second stream of data, is of course the positioning. The satellite ranges interpreted in the form of a location on the ground or in the air, and you add to that the inertial data, which describe the orientation, and then you get your image every second or more. You get your lidar data, much higher frequency, and so on and so forth. But then GPS could get you data 10 hertz or sometimes more. However, inertial data, the typical data frequency or sampling is actually 200 hertz, so 200 times per second. So no matter how your sensor acquiring data, either laser data or pixels, all of that will be synchronized really well and will be positioned extremely well because of the inertial data frequency, which is today 200 samples per second, or 200 epochs per second. And that is on top of the accuracy that you get out of the positioning data, you have the frequency as well, and the time synchronization from your GPS.
Mm-hmm. So to most of us, this just becomes a file which we import into our software and get the correct positions to start with. But there's more to it than that. You have post-processing software that you have to have to come up with the best solution. Is that correct?
Actually, this brings up a topic which is important to address, and I appreciate your question, Eric. Here, um, for some reason, there has been a little bit of misconception around the definition of post processing versus near real time or real time kinematic positioning. So, real time kinematic positioning, abbreviated by RTK, is an excellent way to get all of your information in real time. And the question is, do you produce the maps actually while you're flying the drone? The answer is no. You have to land the drone, get the data, because the data is usually laser scans or pixels or imagery, or both laser scans and imagery. So that takes time to be processed, anyways, to produce the maps. So, why in particular are we focused on RTK with the GPS and the positioning, while the maps are going to take hours and hours for every 10 minutes of drone flight? It's because of the convenience. It's because of that it exists. However, it exists, it works in some solid cases, and it produces accurate results. And this is a very good news for the, for example, the drone society in general, the drone user community in general. And in some applications, it's very, very convenient. However, in certain conditions, like for example, we have a certain error called ionospheric error, which is just a simple layer of the atmosphere from the surface of our planet up to 1,000 kilometers up, or 600 miles. And in that layer of the atmosphere, when satellite signals go through that layer, they get affected and influenced significantly, and it's a very physical phenomena. So we have to work on the data to get rid of that error. It's not that we can get rid of the error by modeling it and something physically. No, it's not, because it changes from the during the day, it changes during the week, it changes during the month or the season or the year. It's 100% physical phenomena. The best model ever that was produced to predict ionosphere was good to like 30-40% of the error, and we cannot afford that. You have a fantastic system called GNSS, and you cannot afford living with a 30% quality. You gotta explore the 100% quality. So basically, physically modeling it doesn't make sense. So working with the data is the only option, and we have multiple frequencies, which is fantastic. It was actually pioneered that way by people who had the vision that they need multiple frequencies from day one. From 1973, they launched the very first satellite with two carrier signals, two frequencies, so we can handle ionosphere. So they knew about this back in 1973. It's not news. And we actually deal with that with the dual frequency on or the multiple frequencies in general on the GNSS system. However, because of that layer of the ionosphere is based on total electron content that is depending on sun flares, we come across something that we face every 11 years, which is the peak of the sunspot activity. So that peak happens to be every 11 years, and then it winds down and then it goes up. That cycle length is 11 years. So it's just a coincidence that this year, 2025, is the peak of the cycle that we have. And that means that the influence of ionosphere on GPS is incredibly high these days. So RTK is not going to capture that, because RTK works in real time. As we mentioned, you cannot predict ionosphere very well. You need to actually model it. You need to work with the data. RTK, when the ionosphere is at the winding down part of the cycle, where the cycle is really relaxed at the bottom there, it works okay. But then with the peak, as we have this year and the next few years, post-processing the data will be better. What does post-processing involve? Just getting the data and go through it forward and backward and learn about the data from the data. So analyzing the signals, understanding them, kicking out the bad signals that got influenced significantly by ionosphere, and then kicking out the ionospheric error by understanding, going through a learning process with the data, and then disregard the errors, or discard the errors, excuse me, this way and end up with clean data down to the centimeter again, where we cannot do with RTK successfully. So I'm not saying that RTK or PPK is better. I'm saying that we need to be mindful of the tools that we have at the right circumstances at the right time. So this time, it's best if you acquire your data and post-process your data, including the trajectory. If you're doing a LiDAR on board an aircraft or on board a drone, or even on board a mobile mapping land vehicle, and you're doing a LiDAR survey or a camera survey, post-process your trajectory in 2025 and 2026, because this is the worst time to use RTK.
Perfect, perfect. Well, and like I say, all of that work to be done to get us a file, which would be for us an EO file to bring in that is tied in the case of our software, it's tied to the images. So it's tied with the center of every image. It gives us roll, pitch, and yaw. It gives us altitude, all of that, so that when we bring the solution into correlated 3D, we've already got a known place to start. So that's fantastic. So let's talk a little bit about integration with sensors, because as you mentioned, we now have people collecting both LiDAR and imagery. That's fairly common at the same time. We also have folks that are very much involved in multi-sensor systems where they may have one or two nadir cameras plus a forward, backward, right and left oblique camera, for potentially modeling situations. When you have multiple sensors, it becomes very, very important for you to know the exact position of those sensors related to each other and related to the aircraft. So fill us in a little bit about that.
Well, this is actually a very important question to address, because the norm today is to have multiple cameras. 20 years ago, single camera did the trick. Even though 20 years ago there were cameras that had multiple heads, but today it is the norm. Every single professional grade manned aviation aerial survey camera has a multi-head camera. And if there is a specific application that needs only one camera, it's considered the custom application, not the standard norm. So multi-head cameras provide like a wide range of information and data streams to the end user. So most of them, they have the RGB and the NIR as well. So you get yourself the infrared data as well as the RGB data. And some people actually do the band stacking, where one pixel carries the RGB and NIR, or they call it sometimes CIR, as in color infrared. So in our case here, all of these data streams to get into, to sit into that one pixel that has RGB and NIR, it means that you're capturing data from multiple cameras that have the RGB nature, the standard RGB cameras, as well as a different camera that is actually NIR. So that's not the same camera that captures both RGB and NIR. They are two different cameras sitting in that box called the system. So when you are talking about those different cameras, some of them have the RGB nature, some of them have the NIR nature, that becomes more of a challenging mathematical and algorithmic approach if you don't have positioning information. So you need to work with all of those multi-streams of data with the mindset that you're integrating, you're fusing data now. You're not using one pixel on one image like the good old days when we had a film camera. You had just one image every few seconds. So today we have multiple images with different nature, and the way to integrate those is to know where every pixel has been captured in 3D space at the moment of the shutter release. And once we know that information from the positioning data, the trajectory data by GPS IMU, you bring all of these data streams together to produce the mapping product or the new modified raw data, like a band stacked image and so on and so forth. So producing a mapping product today from an integrated sensor system is addressing the each pixel where it is, as well as the each laser scan where it started and the orientation of it, as well as mixing all of the above together to produce your mapping product using the trajectory data. Now, the outstanding question is, if I'm doing everything from the air, what about the ground? Like, how do I make sure that my information is correct on the ground? That's why there are certain standards in different countries, but the standards are always asking for comparing the mapping product to an independent source of information. And typically, those are checkpoints. So, what are checkpoints? They're exactly the same as ground control points, but we don't use them in the process. We use them to analyze the map that I produce from the air, whether or not it sits on the right spot on the ground. So, those are checkpoints. That's the purpose of those. And when we do that, we end up with an accuracy report. As we mentioned, that business of geodesy and map projections to map the planet on a piece of paper, that didn't change. Like, even though we are in a digital world, we could actually now work on 3D 100%, not 2.5D. Yet all the algorithms are still kind of stagnant in that 2D world with paper maps, even though we're talking digital maps. And it's going to evolve over time. So people, especially in the large area mapping projects, when you're doing statewide mapping and so on, that footage and nature of the curved earth is going to show up, and errors are going to increase over larger area maps. And that's when people are going to have to work on their softwares to do like real 3D mapping. And that's going to happen eventually. But today we don't have that everywhere in the world. It's still we're mapping on a plane, on a sheet of paper, even though the pixels are digital. So to fix that, we could actually have all of the airborne data tied to one control point to figure out the XYZ deltas of that shift of the datum, and end of story. And then use the rest of your control points as checkpoints. And that's an approach to do your professional grade mapping jobs. Now, let's address potential for the drones. For example, there is some misconception that drones now are doing, this is it, they're doing like precision agriculture, mining, construction surveying, and so on, and that's it. That's not true. Drones are going to be used even more, like a good 100 times more, when we start to tackle the autonomy, like the self-driving vehicle business. Why is that? Well, self-driving is you have a machine to replace you in your vehicle, and that machine needs some knowledge to drive instead of you. So when we drive, we visualize, we actually look at the road and then drive accordingly, knowing what we know about that we can steer, and we could push the brakes or the accelerator and so on. And that becomes more of a muscle memory with us. And now we can chat on the phone, on the Bluetooth, of course, or talk to another passenger and so on and so forth. So this is how we do driving today. The machines will be driving similarly, except for for the machine to see, it will use a map, and they call that high definition map. They abbreviated by HD map. And that HD map is built by a machine, such as an airborne or a land moving vehicle with cameras and lidars and stuff, for the machine to read it. So it's not really 100% mapped, showing the how beautiful the nature around us or the roads and stuff. It just shows certain vectors that the driving machine could understand. That's it. So if you looked at that map, the HD map, if you looked at it, you're not going to like it, because it's just a bunch of vectors. You want to see the reality. So if you're driving over in Italy or Spain, you want to see that beautiful architecture, but it doesn't show in that map. It's just vectors. So those high definition maps, they need to cover millions and millions of road segments, like highways or freeways or city streets and so on, all around the globe. There are certain cities in Europe today that they define whether or not it's a smart city based on the fact that whether or not it includes an HD map, so that the self-driving vehicles could actually leverage those HD maps and do the driving accordingly. And those HD maps need to be produced for the world. So that's a huge potential for the drones. But they might actually produce a byproduct, which is the typical base maps that we could use for surveying and mapping applications to help the infrastructure building and everything. And there will be a lot more updated. And all of those will be over roads. So it makes sense that when somebody is doing the business to do like agriculture, precision agriculture over very simple areas, or mining applications, or construction, civil construction surveys, where the area that they're mapping is usually 100 meter by 100 meter or so, or 300 foot by 300 foot. If they invested that much in a drone, might as well think about the HD mapping for autonomous vehicle, self-driving vehicles, where you could fly over a road segment for 15, 20 miles in one flight, and you need a sensor assembly to actually tackle this properly, and a necessary workflow to process that data.
Fantastic, fantastic. So let's jump into the next subject, which is importing positioning data into correlated 3D, and I'll talk more about this, but it's very simple. In the project setup of correlated 3D, you go through, you assign your images, or, well, one, if you import LiDAR, we don't post-process LiDAR, we bring it as a surface. So if you bring in a LiDAR point cloud, it'll just import it and make it readily available. It'll also ask you if you want an intensity image to go with it, things like that. But what we do is when we select our image folder, sometimes the data, typically, like if you get something out of a DJI drone, it's just going to have the positioning information, lat long, altitude, in the exif file. So now we're not talking about that. We're talking about PPK, post-process results, or RTK results that come in the shape of an EO file. So when you bring in your imagery, all you would do is you would find that file, bring it in along with the imagery, and the software would use that in the AT process. In the AT process, we have three options. There's full AT unconstrained, which means I have EO information. It could be from an EXIF file, it could be from a positioning file, but I want to allow the software to do the math and come up with a solution. The next option is RTK PPK enabled. And that means that you're going to bring in the EO information either in the EXIF file or from a positioning file. And you're going to use the omega kappa phi, the XYZ. The only thing is you're going to say, I'm confident in a solution, but I know there's error in there, or there could be. Therefore, let's allow the software some leeway. Let's use this as the starting point and allow the software to make the corrections to get you the best solution. And we did that because in the drone world, you don't always have the best positioning. And I'll let you comment on that in a second. But then finally, we have direct georeferencing. And direct georeferencing is for our customers that have invested heavily in their camera systems, their aircraft, and their positioning. It is high quality stuff. They're confident in it, and they know it's going to work. So at that point, you're using direct georeferencing, and you're telling the software, everything's fine with my positioning, don't move it, we're going to go with that. So comments on how we do that?
This is actually an excellent approach, to be honest, Eric. I think you guys are the only software vendor in the world that has that open-minded design for the way to handle multi-streams of data. This is the optimal way of doing it, allowing the user to bring in whatever they acquired comfortably in your software environment, and have that flexibility to either 100% depend on airborne data, or let SimActive software work with the data to improve it and optimize different streams, including the EO parameters and so on, or 200% depend on area triangulation. So all of the spectrum there is covered by SimActive, which is definitely appreciated by your user community and your vendor partners, including ourselves and many others in the geospatial world, because of that flexibility and productivity, convenience for your user. So you put your user as your target, which is definitely appreciated. And if you work with the user, you're actually on the right track. And this is what I learned in my career, that when I disappear from the user world for a few days, I'm already on the wrong track, because I'm in the environment of algorithms and scientific stuff that is awesome and everything. But you need the real world influence by the user. You need that perspective of the user. And you guys did that really, really well. And that's appreciated.
Well, I go back to one example you mentioned, and this is the effect of the ionosphere right now, and how it may be affecting people's RTK results. We offer these different ways to process the data, because if you're processing something and you're not getting the result you expect, that could be, it could be from these solar flares. It could be from not having a geoid applied to your data set. But there's a solution in that, and the solution is go to full AT unconstrained and use a ground control point and process the data. If your ground control is off, everything's off 30 meters, then it's probably a geoid offset or something like that. But as you said, solar flare could just affect it by 3 feet, maybe even less. So plan your projects, understand what you're doing, and depending on what the user needs on the other end, maybe 3 foot of error is good enough, and all we're looking at is, like, say, a base map. But sometimes it's they're doing volumes, and they need the tightest result they can get. And if by chance they don't have a full hardcore positioning system, they just have something mid-range, you're probably going to want to use some control to get yourself through that. But we like to provide all those options, and we consider that always a troubleshooting tool for someone. If something's going wrong, just run it full AT constrained, see what's going wrong. You can probably figure it out. So that brings up another question, and we've chatted about this before, and it's quantifying achievable accuracy. So talk a little bit about precision versus accuracy when we're talking about these setups.
Well, to be honest with you, that's a very sensitive topic and needs to be addressed somehow with planning and serious consideration there. So let's start with the precision. Precision, even though the word precision and accuracy in the English language are synonyms, but in the geospatial language, they are not. So precision has been defined as how close the measurements to one another. Accuracy is defined as how close the measurements to the truth. So in my book, precision is the most important first step is to get precision, because you need to have precision in your data. The measurements and information are statistically close to one another. That gives you a really good starting point. And for that, you need the sensors to provide those precise data streams. So if you want precision in your data, you don't want the data all over the place, you want it really sharp and precise, then you focus on the sensor assembly. Then the final step is to bring that precision and put it on the right spot on the ground, which is closest to the truth. That's accuracy, actually. And that's the easy part. That's not the challenging part. You mentioned it, Eric, in the conversation. If you have a geoid error, it will show up immediately. In the United States and Canada and Western Europe and so on, we are blessed with government investments in producing something like geoids and datums and so on. We kind of take that for granted when people talk about the elections and the politicians and so on. But truly, there is serious investment in the civilized part of the world in these aspects, like geoids and such. And droids today are really accurate in the United States, Canada, Australia, Western Europe, and Japan, and so on, because of that investment. That's a lot of tax dollar money invested in there. While in more challenging part of the world, they have bigger fish to fry. They have to deal with survival. They cannot invest in droids and stuff that we invest in. So as a result, if you're operating in the US, you have a way better chance of getting the data and mapping products right on the spot. And because of that investment of the infrastructure, the droid. While if you're operating overseas and you have a data set and they gave you the ground control of the checkpoints, coordinates in northing, easting, and orthometric height, which is the droidal height, then you have so much suspicious. You're suspicious already that everything will fit eventually, because the droid could be biased by meters over in these areas, and you don't have any other option. And they don't even know how to acquire data for those ground control or checkpoints on an ellipsoid. And maybe it's not safe to go out and acquire data again. So in different parts of the world, it's incredibly challenging to work with basic infrastructure that we have here and we're comfortable with, such as the orthometric heights above certain droids. And you end up overseas using those global droid models that are simply nothing but the very accurate droid model in such certain part of the world, such as North America, just extrapolated to cover the globe. So they are very inaccurate around the globe, while they're very accurate around that spot in the North American continent. Okay. And hence people end up with really large errors because of those types of free droids and such. So one of the other options in quantifying the achievable accuracy is the recipe itself. Like, for example, if I'm flying a drone certain altitude above ground that results in the pixel up in the air has a footprint of 1 centimeter. That does not mean accuracy. That does mean only one thing: resolution, which is that if there is any object in the ground that is larger than 1 centimeter, you will see it in the image. If it is smaller than 1 centimeter, you will not see it in the image. That's resolution. While accuracy means that you actually produced a map out of those images, or LiDAR data, or both integrated. That map fits on the right spot in the ground within certain limit of a centimeter. But that 1 centimeter accuracy has nothing to do with the 1 centimeter resolution. So 1 centimeter accuracy will practically include all sorts of errors that you have in the process in one little description or descriptor called accuracy, one little number. So if your accuracy in X, Y, and Z, or northing, easting, and height, or latitude, longitude, whatever description of the coordinate is 1 centimeter, it's just considered as a box that includes all sorts of errors in there. That's 1 centimeter. What sorts of errors? Everything, including your ground control point errors, your pixel resolution, your calibration of the camera, orientation of the camera, as well as the base station. For example, I've heard it many times over the last 20 years since I first, actually 22 years since I first started to join the drone industry in 2003, that people collect the base station data using a good receiver for like 20-30 minutes and then upload the data to the Opus and get the coordinates. That's not good enough, because the accuracy of your base station coordinates depend on how long you acquire the data for. There are many scientific papers out there, and I know that not everybody's going to read scientific paper when they Google how long should I occupy my base station, because it doesn't make sense. You need some convenient information. This is why we're having these kind of conversations, to basically share with our community the information that we know. We need to let it out to contribute properly and connect properly. So many of the analysis done by the United States Federal Administration, called the NGS, part of NOAA, which stands for National Geodetic Survey. They analyzed a lot of those based on so many data sets from the CORS network, and they found out that the best or the least amount of time you need for a good accuracy that is within a centimeter in horizontal and 2 centimeters of vertical is actually 2 hours. So if you are flying your drone, for example, acquiring data for a half hour, just dedicate 2 hours for the job. Go first, set up the base station. Very first thing, set up the base station, turn it on, and then get your coffee, and then fly your drone, and then take a look at the data. Make sure your data is in good shape. You have actually images, and the images are covering all the ground. And then get another coffee, and then pack the drone, and then finally pack the base station so that you give it a chance to have 2 hours. And when you upload those 2 hours data to the Opus or 10-minute data to the Opus, they will give you a solution. They will not say no. Opus will send you an email with that PDF saying, here is your coordinates. But if you send data with 10 minutes only versus 2 hours, you're going to get very different answers. And the 2-hour data will be very accurate. The 10-minute data is not going to be accurate at all. So that base station is going to be everywhere. It's like cancer. The coordinates errors is going to be in your ground control point if you're observing ground control using the same base station. They're going to be in the trajectory of your drone. So that base station accuracy is actually essential to the entire mapping product that you're producing there, and it helps a lot. So that's why my 2 cents here is that when you look at SimActive information, when you look at those summaries of how to use the software, how to use the workflows, when you look at your GPS provider suggested workflows and so on, please read those because they truly have informative stuff to follow, instructions to follow. And once you follow these instructions, your mapping product will be in good shape.
Yeah, you're absolutely right. I mean, it doesn't matter if it's SimActive or anybody else. If it's Trimble with their positioning software, it's got manuals and it's got information in there for you to read, to understand, because they're trying to minimize failure. They want it done right. So in Correlated 3D, we offer an AT report, and as we said, you can bring in your checkpoints, use them and measure against the surface that you've created. You could use them as GCPs. I've always done, I have not lived in a world where I've had the convenience of high quality positioning when I was doing aerial mapping years and years ago. So we had to use control, a lot of ground control, and every once in a while we would find error in there somewhere. And then we'd start playing our game called whack-a-mole, which is to remove a point, process it. Did the error go away? If it did, maybe put it back, go find another control point, move it out of the way, and try to solve for the solution. The approach you have is much nicer. I like it that way. So, I'm glad that we have that. Another thing that we have, because people are using dual sensors these days, and like you said, we're blessed here in the United States with a lot of data. When I mentioned you have the ability to import a point cloud into Correlated 3D from LiDAR, if you happen to collect both, or if you have LiDAR of an area that you've just collected imagery that's within a short amount of time from collection, you can always use that LiDAR for control, at least to, as checkpoints. You can create an intensity image. From that intensity image, you can grab a horizontal value, and from the surface that you create from it, you can grab a. So if you've got nothing except for LiDAR data, you can at least gain some confidence in your solution. So we really like to do that, and I'm always an advocate for having a GCP in there somewhere. But I know, like you said, that you can fill us in on the story, but you don't always need GCPs.
Actually, this is something that I shared once in a workshop in a conference, and I got a lot of laughs at it, which is the United States federal government called NASA successfully sent a bunch of people back in 1969, which happened to be 56 years ago, all the way up to the moon, and they brought them back safely. And they didn't use a single ground control point. So practically it worked. And that was 56 years ago. So I'm sure it will work today. Then for geodesy, because of that business of map projection from the curved Earth to the planar 2D maps, we need one control point. So we're kind of midway between NASA and 100% full ground control. One control point will fix your datum shifts, but the rest is not necessary. So if you're, for example, doing a corridor map for 100 miles and you're updating this on a frequent basis, you can't really establish all of those ground control points everywhere. But you can adjust the datum by one or more control points. And there are so many attempts to analyze that since the first paper came out in 2000, actually, showing that one control point is enough. And that was over from the United States academics, Canadian academics, Australian academics, and then the industry as well. One control point is enough, and people analyze that versus 4 at the corners, 4 and one central point, so 5 and then 10 and then 20. And there's always been the proof that one control point is enough as long as it covers that Earth's curvature to take care of the datum shifts and drifts and so on. So, but otherwise, you don't need the ground control point. Save your money and do something else better with it.
So what you're saying is buy the highest quality positioning system you can get your hands on.
Or sensors in general. Like if you have a camera, improve your camera, improve your sensor assembly. Make your airborne unit easy to use for bigger projects, because autonomous driving, self-driving HD maps are coming. And they're going to be here to stay. And there will be plenty of business for like aircrafts and drones and mobile mapping systems because of that.
Very good, very good. Well, I know we've covered everything in our conversation. I will go ahead and I'm going to jump into a little bit of demo and show folks some of the things that we talked about and how they apply in correlated 3D. But I would like to thank you for your time. We really appreciate you joining us.
Thank you so much, Eric, for including me. It's been such a pleasure. We crossed paths in the last 20 years many times, and I always appreciate your contribution. And thanks for the audience for taking the time to spend that time with us. And I'll see you all later. Thank you. Bye-bye.
All right, so let's get Correlator 3D open. Here we go. Now, I know we spent a lot of time on that interview, so not a lot of time for the demo. So what I want to do is make sure we go over a couple of points on bringing data into Correlator 3D, specifically when it relates to EO information from a high precision IMU. So first we're going to go in and create the project. And I'm going to go ahead and add the folder with the images. There it is. Okay, now we brought the images in, and there is information in the EXIF file, and that information can be seen here. And we've got longitude, latitude, altitude, roll, pitch, and yaw, but I have no idea where those came from. So being that this client gave us an EO file, tells me that they did have a high precision IMU involved, and therefore I do not want to use what automatically appears. I want to use the file they provided. So we'll go ahead and find that file and it here under EO. And look at this, they conveniently gave us the coordinate system of that file as well. I'm going to go ahead and select that. And now you can see things have changed down here. Now it's got the column names, and we have to change this to easting northing to match what they were doing. So we've got easting northing, northing, elevation, and then we have omega, phi, and kappa. And there's kappa down there. Okay, everything's set there. We'll go ahead and select add. And I believe we've got the projection, and I believe that was 6420. California Zone 3, 6420. So we're going to go ahead and accept that. Again, if you have a camera calibration file, you can load that information in. But what we have here is the image height, the image width, the focal length, and the pixel size. That's all we need to get this thing going. So we're going to go ahead and do that. And then we'll just set up a project folder. There we go. And here we go. So now we have our images and they are set up in the right locations. So let's go ahead and open the AT. It is going to ask for type points, which yes, we need. So we'll go ahead and say yes. Okay, now that we have our initial type points set up, let's go ahead and look at the bundle adjustment options as it relates to the type of information you're bringing in. So here we go again. Full AT unconstrained. As I've explained this before, full AT unconstrained means that I am not sure of the quality of the positions that were brought in. So typically you're going to use full AT unconstrained in one of these reasons. You're working with a drone that doesn't have an IMU at all. You're working with a drone that has a poor quality IMU, or you're having issues with the data that you brought in from that precision system. Those are the three reasons you would use that. The second option is RTK PPK assisted. So consider this the one you're going to use with a low grade IMU. The next option is full AT constrained. So full AT constrained means I'm using a Novatel or I'm using a Trimble Applanix IMU. I am confident on that solution and I don't want the software to change anything. Now, that said, you can see here in this little bundle adjustment parameters, you can give it a little bit of uncertainty, okay? So you could say, I'm not sure that the omega kappa phi is right. I want to change it, things like that, okay? So you do still have some ability to do some adjustment there. But this is, again, the solution you would use when you're using a high quality IMU. Now, you'll notice that I didn't bring anything up about the sensor calibration. And that's because it's separate from the positioning, right? So sensor calibration means that I've got I imported a calibration file that I have done previously. I know it works and I'm going to use that. So then you would use constrained and that constrains it to those calibrations. Unconstrained is typically what we use, again, in the drone world and so forth, because the cameras just aren't that high precision. You might use constrained when you're using a phase 1 camera or a Leica camera or, a ZI camera, DMC, whatever. In that case, you would use that. So those are the options when you're doing the bundle adjustment. And then that's what the sensor calibration is for. Well, the interview was long, so the demo was short today. I'd like to thank my guest, Mohammed, for joining me. Thank you. I'd also like to thank those who attended the webinar. Again, if you submitted a question during the webinar, I'll make sure to get those answered for you as soon as possible. I'd also like to remind everyone that this webinar, as well as all of our previous webinars, are available on our website, simactive.com, where they can be found under the Learning tab. Additionally, this webinar will be converted to a podcast and made available in the next few days. Thanks for joining us. Until next time.